So this is a new week, and so we have a new data set, and as always, you can download it. This data set is about credit card fraud detection, so I'm loading it up. I'm doing my train test split. It's a pretty big data set, 240,000 credit card transactions, and they're not really telling us what these features are. They just kind of already processed some features for us. But we have a time, we have a bunch of these numerical features, we have the amount, and we have our class, which is our target, which is, was this a fraud or not? So these first five are all not fraudulent transactions. And so we want to learn from these anonymized features about a credit card transaction. Was it fraudulent or not? And yeah, we need to think about this time variable. So like, do we want to scale time? Time is sort of a special feature, and we have a lecture on that later in the course. And so we're just going to not worry about it too much for now, and we'll come back to that later. Okay, so we start with our dummy classifier, and we see something kind of unusual that we haven't seen before, which is that dummy classifier seems to be doing awesome. It's getting 99.8% accuracy. And I mean, this was supposed to be like a silly just thing that is totally ridiculous that predicts the same thing every time, and yet it's getting almost perfect. So that's what today's class is going to be about, what is going on here. And the reason why that's happening is because we have 241,000 legit transactions and 413 fraudulent transactions. And that makes sense. I mean, most credit card transactions are not fraudulent, I hope, right? So if you collect a data set of credit card transactions, most of them are not going to be fraudulent. And so this is called an imbalanced data set. We have way more examples of kosher transactions than of fraudulent transactions. And that's going to bring up some challenges that we're going to be addressing today. So it brings up this question of what is a good accuracy? Is 99% a good accuracy? Is 99.9% accuracy? I mean, for this problem, apparently 99.8% is not really very good. And that's why we always start with dummy classifier, just to see what we're dealing with. But there's another question here, which is that maybe accuracy just isn't a useful measure at all. And today we're going to talk about other scoring metrics other than accuracy for classification. Okay, so I'm going to make a logistic regression pipeline that is scaling followed by logistic regression. And I'm going to compute the score. And it just takes a couple seconds because it's a bit of a larger data set. And so, okay, I mean, we did improve from 99.8% to 99.9%. So I guess logistic regression did do something, but I feel like we're kind of operating in the dark here because we just have no clue. Like, should we be happy with this or not? At least I have no clue. Like, okay, I'm the bank. Someone comes to me with this. Is this good? Should I use this fraud detection system or should I not? And so, yeah, let's get into some tools. What I'm going to do today, even though we don't usually do it, is instead of doing cross-validation all the time, I'm going to actually split into the training portion and the validation portion. So I'm just going to do one split of 4/5 that I'm going to call the train fold and 1/5 that I'm going to call the validation fold. And I'm just going to do everything that way, and it's going to be a bit easier code-wise because scikit-learn with the things we're going to do today with cross-validation is a bit clunky. So we're basically just doing one fold of the 5 or 10 or however many folds, and we're just going to look at that for today. And it's not too worrying because we have a big data set, and so the randomness of the split is not going to be as problematic as with the smaller data set. So you could do it manually with just raw Python, or you could actually do another train test split. We usually use that for the stated purpose train and test, but you can use that same function to split the whole training set into the training fold and the validation fold. Either one of these is going to accomplish the same thing. Okay, so yeah, I'm going to use X test as the test set, train is the entire training set, and then train fold is like the train 4/5 of that, and valid fold is the validation 1/5. And so I'm going to fit my logistic regression just on the train fold, which is actually what was happening under the hood with cross-validation. And then I'm going to make this new thing, which is our first topic of today, which is a confusion matrix. And so here's what this thing is. It says, instead of just looking at accuracy, which is number correct and number incorrect, let's break it down to what was the true class, non-fraud or fraud, and what was the predicted class, non-fraud or fraud. And now the diagonal elements here, true, not fraud, predicted, not fraud, and this one, true, fraud, predicted, fraud, those are the correct cases. Those are the ones I got right. And the off-diagonal ones are the ones I got wrong. And this paints a more informative picture for us than just looking at accuracy, because we can actually see what's happening. For example, we can see that of the ones that were not fraud, we had 23 false alarms where we accused the person of fraud wrongfully. And of the fraud ones, we weren't actually that great. We only caught about 2/3 of them. So there's of all the frauds, for 1/3 of them, we just completely missed it, which isn't super awesome. I mean, we kind of want to be catching these frauds, or our client's going to be upset because they only find out later or never notice or whatever. And that's our job as the bank to make this number smaller, right? We want to be catching these frauds. And if we make this number bigger, it's going to inconvenience our customers because your credit card gets blocked. You have to call them. Yes, it was me. Yes, it was me. But maybe it would be worth trading off having some more false alarms in order to catch more of the frauds. And that's a very big theme of what we'll be talking about today. So this was made on the training set. This is like the training accuracy. I can do the same thing for the validation set, and this is like the validation accuracy. You can see all the numbers are smaller here because our validation set is 1/4 the size of our training fold. And it's the same sort of pattern where of the ones that are fraud, we're really not doing a good job catching most of them. I'm just saying that there's like the fancy scikit-learn function that makes a pretty picture, and there's kind of the base scikit-learn function that just gives you a NumPy array, in case that's useful to know. Important to note that there's different conventions for the confusion matrix. Scikit-learn has the true one here and the predicted ones over here, but sometimes you see it the other way around, where it's the true ones on the bottom and the predicted ones on the side. So you really need to know what type of confusion matrix convention you're dealing with so you're not reading it backwards. So just a heads up about that. Okay, so some new terminology. Again, here we have the predictions, here we have the true things. So we have these 4 terms. True, negative means, okay, first we need to talk about positive and negative. So for today, we're going to have a class we call the positive class. That's like the thing we're trying to detect, in this case, the fraud. Or in medical diagnosis, it could be like the person is sick. And negative means it's fine, there's no fraud. So true negative means it was negative and we got it, we predicted negative and that was true. True positive means we predicted positive and that was true. False positive means false alarm. We said it was fraud, but it was just a false positive, false alarm. It wasn't really a fraud. And false negative means we said it was okay, but we were wrong. It was actually not okay. So those are 4 terms that are pretty often used and useful for you to know. And just a quick note that we've only been talking about binary classification in this whole course so far, with just 2 categories: fraud, not fraud, high income, low income, cilantro, no cilantro. But there is multi-class classification that's super common, where you could have, say, 3 categories, and you can still have a confusion matrix in that case that just says if it was this and predicted that, if it was this and predicted that. And we'll mention multi-class classification later in the course. Any questions about this so far? Okay. So moving on. We said before that accuracy was maybe not that useful of a metric here. And so we're going to introduce some other new metrics. And the first two things we're going to talk about are precision and recall. And so recall says, how many of the actual frauds did we identify? And precision says, of all the frauds that we identified, how many were real? And so going back to this plot here, the recall is said, okay, of this bottom row here, of the ones that were actually frauds, how many did we correctly recall? How many did we identify? Which is 54 that we found out of 84 in total. And so our recall score here is 64%, which is pretty bad. That's like, we only found 64% of the frauds. I don't know if this is the greatest fraud detection system ever. And yet, the accuracy was 99.9 because almost all of them are not frauds, and we're identifying them as not frauds. And so this score tells the story a lot more than the 99% accuracy. The other one is precision, which is saying of the ones that we said were fraud, of this right side here, how many were actually fraud? So the distinction between precision and recall is a bit subtle, but again, recall is of all the frauds, how many did we catch? And precision is of all the predicted frauds, how many were actually frauds? And so that's 54 out of this 64 that we predicted fraud, if we add up this whole right column. And so our precision here is 84%. So that means 16% of the time we raise the alarm, it's a false alarm, and 84% of the time we raise the alarm, it's a true alarm. I've mentioned this terminology document before. There's so many terms in this case. So you might have heard sensitivity, specificity, type 1 error, type 2 error, all these kinds of things. And you can take a look at that terminology document if you want more details about all the terms. So an important question is, which metric do we actually care about? I mean, we'd love to have 100% accuracy and precision and recall and 100% everything, right? But we can't. And so what do we actually care about? And furthermore, if we could tip the scales, which we'll talk about later today, if we could tip the scales towards predicting more frauds, that means we would have more recall, but we would also have more false alarms, lower precision. So if we could make recall go up and precision go down, should we? And that is totally an application-specific decision. That it's not like a mathematical question. It's a, well, what are we doing here question. The bank has to decide, well, how inconvenient is it to cancel someone's credit card when there's no fraud? How inconvenient is it to miss a fraud? And kind of pick that trade-off. So in this case, I would say maybe they probably want higher than 64% recall, and they might be willing to tolerate more false alarms, but who knows? Okay, so often we need like a single score, like precision and recall are 2 scores, but often we just need to reduce everything down to a single number. For example, if we're doing hyperparameter optimization, or if we want to rank different models, we just need a different number. So F1 score is one possible alternative. That's just like a single number average of precision and recall. You can see the exact math in the Wikipedia article, but it's kind of like the multiplicative average of precision and recall. And the point is, if F1 score is better, that indicates that precision and recall, or as precision and recall get better, the F1 score gets better. Say it like that. So yeah, it may often be that for what you're doing, F1 score just makes more sense than accuracy, because just talking about 99.9% versus 99.999% is kind of confusing and misleading. And so we'll talk about other scores later today, but I want to show you some scikit-learn functions. So one is the classification report, and that one just prints out a whole bunch of scores that are kind of useful. So one important thing here is that we have decided that fraud is like the important class, or the positive class, or the one we care about. And so we care about this row with 84 frauds, precision 84%, recall 64%, F1 score 73. But if not fraud was the positive class, then it's giving you information for that too, which we don't really care about here. But just to let you know that, yeah, if we really care about not frauds, then basically we're doing great, but that's not actually what's happening here. So this is our confusion matrix again. Here I just took the same thing but printed it out to 4 digits. I just wanted to point out these are not exactly 100%, but they're just very close from what we saw above with 2 digits. Okay, not that important. My colleague Verida created this cheat sheet, which you can refer to later. That's just a really nice summary of all these things. So feel free to refer to this when you're working on this stuff. So there's a nice example and everything. All right, questions? Everyone's quiet today. Okay, here we go. The plot thickens, precision recall curves. So this is where it gets interesting. We talked earlier about predict and predict proba. And we said predict proba returns this number. I don't really want to call it a probability, so I'm going to call it a probability score. But it is this number between 0 and 1 that indicates some level of confidence coming out of the model. And a bunch of scikit-learn classifiers have this. Logistic regression has it, and some of the other ones we'll talk about on Thursday have it as well. And yeah, it's a score that will basically tell you the higher the score, the more it thinks the thing is a fraud. And that's actually pretty useful for the bank, right? It would like to know that number. And furthermore, one way of thinking about predict is that predict, and when you implemented dummy classifier on homework 3, you might have actually implemented this way, but I like to think about predict as it just calls predict proba, and then it thresholds the result at 0.5. And this is for binary classification that we're talking about today, just 2 outcomes, like fraud and not fraud. If that score is 0.7, it's going to say fraud. If that score is 0.2, it's going to say not fraud. And just a reminder that predict proba actually gives you 2 columns. It gives you the score for not fraud and the score for fraud, and they add up to 1. And today I'm just going to be talking about that second column, the score for fraud. So how much does it think there's a fraud? So here's an important question. What if we said earlier, maybe I would like to catch more frauds? What if I just change that threshold? What if I say, if the probability score is 0.3, I'm going to cancel the credit card. Or if the score is 0.2, I'm going to cancel the credit card. Well, what that's going to do is it's going to help me catch more of the frauds, because some of these where I missed the fraud, they might have had a score of like 0.4. They were kind of close to the edge. And if I lower the threshold, I could catch these. But I'm going to create more false alarms as well, because there might also be some that I was previously getting right and saying this is not a fraud with a score of 0.4, and I'm going to start raising the alarm on those as well. So here's our precision and recall that we saw a few minutes ago, and I could get those predictions. So notice that these scikit-learn functions are taking in the true thing, y value, and the true class and the predicted class. I'm calling predict, but I could generate these predictions, as I said earlier, by calling predict proba. This :1 says take the right column, take the column for the fraud score as opposed to the non-fraud score, and just say, is that bigger than 0.5? And I'm going to get exactly the same thing. This is this is generating the same predictions as just calling predict, because that's basically what predict does, if you want to think about it that way. So yeah, what if we change the threshold? What if we make the threshold 0.8 and we say, no, you got to be 0.8, otherwise I'm not considering this a fraud. I'm going to be really strict. Well, that's going to make the recall worse, because it's going to say, well, I'm not voting fraud as often anymore because I have this higher bar that I have to clear of 0.8 before predicting fraud. But at the same time, our precision is going to get better. But it didn't. And okay, let's ignore that for now. I have some notes about that. Yes, I know why this is happening, but I don't want to talk about it right now. Okay, so let's instead have a lower threshold. So remember, 0.5 is the standard value. And so what I'm going to do now is I'm going to threshold at 0.1. And so remember, before our recall was 64 and our precision was 84. But if I threshold lower, my recall goes up and my precision goes down. And so what this is saying is I'm going to just be very trigger happy and be predicting fraud very easily. The score just has to be more than 0.1. And so, yeah, I'm going to catch more frauds now, but I'm going to also have more false alarms now. And there's this curve that we can draw called the precision recall curve, which what it does is, you saw me changing the threshold from 0.8 to 0.5 to 0.1. The way this curve is generated is it's sweeping that threshold. It's making it like 0.01, 0.02, 0.03, 0.04. And every time it's sweeping the threshold, it's putting the precision and recall, and it's putting a dot on this graph, and it's connecting them with the line. And so, for example, so the thresholds themselves are not shown on this graph. You could have another graph with threshold on the x-axis and precision and recall both on the y-axis. But what this plot is doing is not showing you the threshold, but each of these points along the line has a different threshold, and we can see the precision and recall kind of changing. And this thing right here is kind of that weirdness that we talked about, that the recall and the precision both went down as I moved this way, which I don't want to talk about right now. But yeah, there's some notes about it below. And this star that I drew is a threshold equals 0.5. That's like the default behavior, which is when you're just calling predict. And if you look, the star is at around recall equals 64 and precision equals 84, which is what we saw earlier. But you could set the threshold to anything you wanted. So you could say, hey, I want a higher recall. Okay, what's it going to cost me? Well, if I want the recall over here to be, 0.75, then my precision is going to go down. I'm going to catch 75% of the frauds, but of the ones that I said were frauds, now only 80% are actually frauds. And now look how much it costs you to move to recall 85%. If I want recall 85%, now I'm in a disastrous situation where of the ones that I say are frauds, only 10% of them are actually frauds. So I probably don't want to pay this steep price here, but I don't know, maybe where you want to operate along this curve, what threshold you want to use, it's up to you. And it really depends on your application area. But if this whole curve is unsatisfying to you and say, no, this is junk, I want to be up here where my mouse is not on the curve, I want 90% each, otherwise my boss is going to be upset, well, then you need to think about a different model. Maybe you need to change your hyperparameters. Maybe you need to abandon logistic regression, because what you're doing is not offering you that option. It's just not good enough. But a better model, better preprocessing might offer you just a better curve overall, where you can pick a spot up here and satisfy your requirements. This AP here is kind of like a single number. It's called average precision. It's basically a single number summarizing the goodness of the whole curve. So if you had an amazing model that was like up here, it would have a higher AP because it would be a better curve. And so you can just compute that directly with scikit-learn. Yeah, we're not going to talk too much about that. I don't have a Q&A here, but I think this would be a good time because this curve is kind of a big concept. Are there any questions about this curve? The red star is where the threshold is 0.5. So remember, the threshold is changing along this curve, although it's not shown. And the red star is kind of the default behavior where the prediction comes from thresholding the probability score at 0.5. And so that's just the default. That's what's going to happen if you call.predict. What's the difference between precision score and average precision score? Okay, great question. So precision score is for a particular model. Precision score tells you how good is predict. So you make your predictions and you compute your precision score. Average precision score is assessing how good is your predict proba, because it's taking all the probabilities and saying, let's consider all possible ways of thresholding those probabilities. And basically, if all the frauds had high probabilities and all the non-frauds had low probabilities, then this score would be really good. And so, yeah, they're actually measuring different things. One is measuring how good are these probability scores, and are they kind of ordered properly? And precision is just measuring, or recall is just measuring for a particular set of predictions, which implies for a particular threshold, how good are they? Is most of ML research just creating classifiers? I assume you mean new classifiers like an alternative to logistic regression. No, there's a lot more to it than that. I think that would be a great post for Piazza, and I'd be happy to elaborate on that. Is AP similar to area under the curve? Yes, it's kind of similar to that, and we'll talk about that in a few minutes. Can I explain why the precision score went down from that point before? I'm going to leave that for now. I have it in the notes. The threshold. Okay, yeah, what is the threshold? So it's this number. It's what you look at the probability scores, which are between 0 and 1, and to get predictions like fraud or not fraud, you got to threshold them somewhere and say if the probability score is above 0.5, that's a fraud. No, wait, if the probability score is above 0.1, that's a fraud. And so we can choose that threshold. Why is the line not bumpy here? Yeah, so we have to think about it. So precision 1 means everything you're saying a fraud is a fraud. It might be the case that, so I got to think about this. And yeah, so it's probably what's happening is that it's like, I recall 0.2. So maybe here you are only predicting like 5 frauds and one of them is an actual fraud, and maybe here you're just predicting 4 frauds and all of them are. I know I'm confusing myself. Let me answer that later, or maybe she can answer it in the chat. I don't want to run out of time. I'm just reading the chat. Could it be the start of the data and all of it is actually correct? Yeah, okay, that's attempting to answer this question about this flat part. Okay, let me move on. So, oh, and this is actually relevant to the discussion we just have. So this AP versus this F1 score. So it's very important that when you're thinking about a metric, you are thinking, is this metric assessing the goodness of predict, or is this metric assessing the goodness of predict proba? And so far in this course, we've only talked about accuracy, and accuracy is in this first category. Accuracy just looks at predict and says, is this one right? Is this one right? Is this one right? Is this one right? And gives you a % correct. And I keep mentioning the threshold because predict is just predict proba but thresholded. And so in a sense, things like F1 score and accuracy are a function of your scores and also the chosen threshold. Whereas this one is a summary across all possible thresholds in a sense. And so it doesn't care what your threshold is. Okay, yeah, so this whole thing of the curve going down when you think it would go up was asked on Piazza last year, and then I pasted in a paraphrase of the question, my answer last year. These things are very confusing, and I don't want to go into it too much right now, but take a look through this and we can follow up on Piazza if you want. I'm just afraid that if I go down this, I'll waste a bunch of time in class. Any other questions before we take a break? Okay, let's take a break. And, oh, there's a question. So we go through all of these F1 and AP when we have an imbalance in the classes, right? So you can compute these scores anytime, but accuracy becomes a particularly bad measure, or it doesn't really tell the story when you have this kind of severe imbalance like that. And so this is a good time to start thinking about these things. That said, even if you don't have that much imbalance, if you really care about producing good scores out of predict proba, then maybe you want to use some of these things like average precision score, even if you don't have imbalance, just, and we'll talk about another one after the break called AUC, but maybe you want to use these types of measures even if you don't have imbalance, just because you really care about the quality of your scores more than the quality of your predictions. Okay, let's take a break until 11:45, and I'll see you then. All right, we are back. Just over the break, I was thinking more about this thing and reading my own answer from a few months ago. And to just quickly summarize, when you make the threshold lower, you're basically always going to predict more positives. And some of those might be actually positive and some of them might be actually negative. And so the recall is going to stay the same because the denominator of the recall is just the number of positives, which is fixed. And then the top is how many did you find, and that could only go up. The reason why precision can go down is the denominator is the number of predicted positives. And so that denominator can actually go up when you lower your threshold, but the numerator might stay the same. So if you lowered the threshold and you now predicted way more positives, but all of those were actually negative because your probability scores were not very good, then your precision is actually going to go down because you lowered the threshold, started predicting more positives, but those were all wrong. And so now you've gotten the same number right over a larger denominator, and so the precision goes down. So that was this behavior over here that we saw the precision going down when the recall also went down. So we just had, in between these two thresholds, we had a bunch of bad probability scores, basically. Okay, let's keep going. So next thing we're going to talk about is an ROC curve. ROC stands for receiver operating characteristic, which is some old communication theory thing, but we just call them ROC curves. And that's very similar to a precision recall curve, but just with different axes. And so ROC also plots recall on one, but it plots the false positive rate on the other. And so this is the number of true positives over the total number of positives, and the false positive rate is the false positive over the total number of negatives. And so this doesn't have this behavior that we just talked about where it could go down when you think it would go up, because this denominator is just number of true positive, is number of positives, it'll never change, and this denominator is the number of negatives, it'll never change. And so as you change the threshold, only the numerators are changing. And this is always going to go up and this is always going to go down, or vice versa. So, so an ROC curve looks kind of like this. And so this true positive rate is another name for recall. So this is recall over here. Again, it's the same type of thing. It's changing the threshold, but it's just different axes. I know both of these types of curves are confusing, but they are useful summaries of how good your predict proba scores are. So again, here, as you move the threshold, your recall is going up. So you're lowering the threshold, you're predicting more frauds, therefore you're finding more frauds. But now on this axis, instead of precision, you have, well, of all the ones that were not fraud, how many did you incorrectly say were fraud? And so that's kind of the false positive rate or the false alarm rate. And so here we're saying, well, our recall is 64%, but we're not having a lot of false alarms. Here we're saying our recall is now higher, say 90%, but 20% of the alarms we're raising are false alarms, et cetera, et cetera. And we can adjust this by moving the threshold. So precision, again, precision was saying of the number of alarms you raised, how many were false alarms? And this false positive rate is saying of the number that were reasonable, not frauds, how many times did you raise the alarm? So they have different denominators. Yeah, so here you want to be, your kind of dream situation would be to be in the top left, which is you're getting everything exactly right, 100% recall, 0 false positive rate. And again, you can compare these different curves for different models. So maybe the logistic regression is doing this, maybe you change the hyperparameter, it's down here, and then everything just seems worse, et cetera, et cetera. So which of these curves you want to look at? They say slightly different things, and it basically depends what you care about for your particular application. And again, these curves are basically assessing how good is your model at generating a good predict proba function. And a good predict proba function is ones where the frauds have very high scores and the not frauds have very low scores. Someone asked, wouldn't being at the top mean we're overfitting? So keep in mind that I'm making all these pictures with the validation set. So this is not, I'm not looking at these plots on the training set, I'm looking at them on the validation set. And so if I'm getting 100% here, that's like 100% validation accuracy, which is great. So I wouldn't necessarily be overfitting there. Okay. And again, the red star is basically the default of calling predict, which is the one we saw. Okay, I'm just gonna move to some of these animations that I think are quite useful. So let's give us a couple minutes to digest these animations. So what's actually going on the x-axis here is the output of predict proba. Whoever made this animation had this as an input or a feature, but we can think about this as this x-axis is the output of predict proba, and you could think of, say, 0 over here and 1 over here. And so what we have here is this very useful type of picture to look at. And on the homework assignment, you're going to make the same type of picture for the problem you're working with on the homework. And basically what it's saying is, let's look at a histogram of all the probability scores for frauds and for not frauds. And let me actually start with the second. Let me start with the second one. I think this is actually maybe a better place to start. So think about it like this. If these two histograms were very separated, like they are here in this moment, if they're very separated, what that means is that for all the frauds, all our scores are really big. Like for all the frauds, predict proba is always outputting, say, between 0.8 and 1. And for all the not frauds, predict proba is always outputting say between 0 and 0.2. That's basically the dream situation. That means everything is perfect. You just threshold somewhere in the middle, like 0.5, classify all the frauds correctly on one side, classify all the not frauds correctly on the other side. So a mindset to think about what is imperfect about what we're doing here is that those two histograms are actually kind of overlapping, which means we have some cases where it's really a fraud, but predict proba is outputting 0.2, or it's really not a fraud and predict proba is outputting 0.7. And in that case, there is no threshold you can choose that's going to get both of those right. And the more overlapping we are, if the two histograms are completely overlapping, meaning that for frauds and not frauds, it's giving you basically the same distribution of probability scores, that's basically a useless classifier. It's not really, there's no way you can threshold that and do a good job of separating the frauds and the not frauds. And so, again, the way this kind of overlap situation looks depends on your data set, but also depends on your pipeline. And an amazing, super good thing is going to separate the two classes more. But then again, going back to this first week of the class, we talked about there's kind of a best error. There isn't necessarily any classifier out there that'll perfectly separate them and get 100% accuracy, but you can always try to do better. And so now let me go back up to this animation. What this animation doing is it's showing kind of a realistic case. So the blue histogram, those are like the probability scores for the frauds. And again, we should think about these axes as like going from 0 to 1 here. And the orange, should think about as the not frauds. And so these ones over here on the far right, this situation over here is great because it's basically saying the really, really high proba scores of like 0.95 or 0.99, that's going to be great. We're going to catch those frauds, and there's no not frauds that have such a high score. There's no not frauds that say 0.99 chance of fraud because our classifier is not that crazy. And so if we draw the threshold maybe right here, then we're going to get 100% precision because we're going to predict only this blue stuff as frauds, and we're going to get them all right because they're all frauds. But we're going to have a low recall because all the blue stuff below this line, we're going to miss because those have lower scores than the threshold. And so what this is showing is that as you sweep this line, which is this threshold, you're making this trade-off between precision and recall. You could set the line all the way to the left, and that's just saying I'm going to predict everything as a fraud. And I mean, that's fine. You get 100% recall, but you get very bad precision. And so this is kind of a joint animation showing an ROC curve. And as you're sweeping the threshold, which is this line on the left, it's moving the red dot on the right and kind of illustrating that each point on this ROC curve corresponds to a particular threshold. And as you move that threshold, then you get different trade-offs between the, in this case, recall and false positive rate. And so going out to these flat things earlier that we talked about, so what we can see here is that this flat part over here is basically a part where you only have blue. So you can basically just get free correct answers without getting any incorrect answers as you move the threshold up until you start to hit the orange. And then you're starting to make some incorrect predictions because everything to the right of the line you're predicting as fraud, and everything to the left of the line you're predicting as not fraud. Okay, that was a lot of me talking. Let's have some questions. Here, a complete overlap means that the chance of being a fraud would be random. No, a complete overlap means your classifier is basically useless at detecting what is a fraud or not fraud because it seems to give the exact same proba scores for frauds and for not frauds. And so the classifier is kind of useless. A good classifier would give higher proba scores when it's a fraud and tend to give lower proba scores when it's not a fraud. So it's not saying something about the data necessarily, but it's saying that the classifier is not doing anything useful. Yeah, so the ROC curve being a straight line is basically that complete overlap situation. Yeah, you can think of it as a worst case. Yeah, if we get a complete overlap, then yeah, sure, you should try a different classifier, and you'll see it yourself. I mean, you'll compute the scores, and they won't be good, right? You'll have, say, like 50% precision and recall or something like that. Yeah, okay. Just as sort of meta commentary, I don't know. I always I feel like this is very confusing for students, which is usually some combination of it is confusing and I haven't yet mastered the best way of explaining it. So every year I chip away at some things and I'm like, okay, this year I figured out how to explain this thing particularly well. I'm still not super satisfied here, but I will keep working on it. And it is also legitimately confusing. So please don't hesitate to follow up on Piazza, and we can talk about this more. There's another question. Okay, so this AUC is the area under the curve. And so as we said before, a great curve would just basically go all the way to the top right. And so the more area under the curve, the better the curve. So the straight line is kind of a bad curve and more to the right is a good curve. So you can look at the area under the curve. And again, we talked about having a single number that's a score for the whole curve. The area under the curve is kind of a single number. It's very similar to the AP that we saw before, the average precision. It's a single number telling you how good are your predict proba scores. And so it's common to look at these as opposed to, say, accuracy. Another question. So blue here is representing frauds and orange is representing not frauds. And these are the different predict proba scores coming out. So I'm going to move down to this other plot. This other plot is kind of showing the same thing. I don't know why it's changed from orange to red, but in any case, blue is the fraud, red is the not fraud. And what it's showing is that if your classifier can pull these apart, you're going to have that perfect ROC curve, and you're going to be able to get 100% accuracy, 100% precision, 100% recall, because when they're fully apart, you just set this threshold in the middle, and you make no mistakes on one side, and you make no mistake on the other side. But in reality, even for a decent classifier, you're going to have these overlapping cases where you have a non-fraud with a higher score than a fraud, and then there's just nothing you can do. Because whatever threshold you pick, you're going to make some mistakes one way or the other. So this ROC, AUC, again, AUC is area under the curve. You can also compute this with scikit-learn and it'll tell you how well you're doing. And in this case, it tells us we're doing pretty well. It tells us we have a good area under the curve. The average precision score that we talked about later may be more appropriate when you have imbalanced data sets as opposed to the ROC, which could paint a rosy picture due to the class imbalance. Okay, so I just linked to an article here if you're interested, talking about why precision recall curves are preferred for imbalanced data sets. What does density mean? So these are histograms of the probability scores. So on your homework, you're gonna compute these histograms yourself, and maybe then it'll make more sense. But it's basically saying there's a lot of, for the frauds, you have a lot of scores around this value and not too many scores around this value, and so on and so forth. So it's basically plotting a histogram of the predict proba scores. Let me, will class imbalance most likely be detected when we have a high score with dummy classifier? Yeah, correct. I mean, you could look at just the frequencies of the different Y values. So you could say I have 240,000 frauds, 500, 240,000 not frauds, 500 frauds. Bam, that's imbalance because I just have way more not frauds than frauds. And dummy classifier is going to tell you the same thing. It's going to get a high accuracy. But yeah, you can simply look at the number of frauds and not frauds you have in your training set. So let me just, okay, I want to keep going in the interest of time. So let's keep going. So far, so I want to talk about addressing class imbalance. And basically, we already talked about the fact that you can adjust the threshold, which is a reasonable thing to do. I'm going to talk about a way of doing this that is kind of easier in scikit-learn, but basically the same thing. So we'll get to that in a second. But first of all, again, this value counts function and Panda is just going to tell you, okay, we have 240,000 not frauds, 400 frauds. And we're having all these issues. So accuracy is not really useful. We want to look at precision recall. Suddenly we're thinking a lot more carefully about predict proba rather than just predict, because maybe the bank, or maybe in your application you only want to flag it if you're really sure, or maybe you want to flag it conservatively. We made this confusion matrix. We kind of thought about these and said, do we care more about this type of error or that type of error? And again, that depends on your application. And so one thing we can do in scikit-learn, of course, you could just use predict proba and then threshold it yourself, and that's totally fine. However, if what you're doing would be, if you want to keep using .predict, then .predict thresholds at 0.5. And as far as I know, there's no like parameter you can pass to .predict that says threshold at something else. And so the way this is handled in scikit-learn, if you actually want to use .predict and you don't want to use predict proba and threshold it yourself, is something called class weight. And so what class weight does here is it says class number 1, which is the frauds, because they're just encoded as 0 is not fraud and 1 is fraud. So we're saying for class number 1, I want to give it a weight of 10. That means the frauds are 10 times more important to me than the not frauds. Or I'm going to be 10 times more upset if I mess up one of the frauds than if I mess up one of the not frauds. And so it is a way, is an alternative way. You can call predict proba and use a really low threshold, and that'll help you catch more credit card frauds. Or if you want to keep using predict, you can set this class weight, which is going to actually change the scores coming out of predict proba. So instead of changing the threshold, instead of making the threshold lower, you're going to make all the scores higher and keep the threshold at 0.5. And you're going to see that on your homework as well. You're going to change class weight and you're going to actually look at the scores and you're going to see that they got higher. So if I do this and then I make my confusion matrix, what you can see is of the 84 frauds, there's always going to be 84 frauds in our validation set. We can't change that. But of these 84 frauds, before we were catching 54 of them, now we're catching 67 of them. So we're getting a higher recall. But on the other hand, before we had 10 false alarms, and now we have 23 false alarms. So it's really the same as changing the threshold. It's just causing you to say more things are fraud than you were saying before. But again, just to reiterate, when you set class weight, it's actually changing the scores that come out of predict proba and keeping the threshold at 0.5. So let me write that down. Instead of changing the threshold, we boost up all the scores from predict proba and keep the threshold at 0.5. Instead of, either way, we end up. Okay. Yeah, so class weight is kind of a simple scikit-learn thing. You just add class weight and then you're done, basically. There's some fancier approaches to imbalance. There's something called SMOTE that I linked to here. We're not going to go into this course, but this is something that people think about is kind of how to deal with this imbalance, other than just changing the threshold. So another useful setting of class weight in scikit-learn, you can just say make this weight of 10, but there's a special thing called class weight equals balance. And what that basically does is it says, hey, you have 400,000 not frauds and 400 frauds. Okay, that's 1,000 to 1 imbalance in your training set. So I'm going to set the class weight of the frauds to be 1,000 times more to kind of counteract that and kind of make it as if your data set had half frauds and half not frauds. And so I do that here. I set class weight to balanced. And then I can fit it. I can do the confusion matrix. And here you can see a stronger shift towards fraud. So here it's kind of like saying here that both two kinds of mistakes are similarly problematic. Not exactly, but it's basically like a predetermined reasonable amount of extra weight to shift things so that you don't have to decide on what threshold to pick. And so here you're now getting, it's kind of a nice default, I guess I would say. So here you're, of the 84 frauds, you're catching 78 of them. I guess that's pretty good. But on the other hand, you have 1,000 false alarms. And so you can use these things if you want, or you can kind of do it yourself by fiddling with the weight or fiddling with the threshold. At the end of the day, they're all kind of doing the same thing, which is controlling this trade-off between precision and recall. And if you just want everything to be better, you have to try a different approach. And then maybe you can also get everything to be better. Questions about this? Just reading through the chat, seems like the questions are answered. Yep, C is 1 in logistic regression. That's the default, but we can change that and things might get better. Let's say we have a huge data set. Would it be possible to make it so it's close to 100% accuracy? Well, not really. I mean, logistic regression might just be underfitting, for example, and it's not really an issue of your data set. So I would say if you have a huge data set, then, and you combine that with like a really good pipeline, then you can get really good accuracy. But a huge data set with a not very good classifier is not really going to solve the problem. Okay, I didn't really understand the follow-up, so I'm just going to keep going. Another question, is class weight another hyperparameter we should tune? See, that's a very interesting question. I would say, so I do actually have you tune it in the homework, but I would say it's really more of like, okay, there's two ways of thinking about it. One is that you're going to find a score that is like the score that you really care about, like maybe F1 score. You just decide, from what I'm doing, F1 score is the be all and end all, and I just want to make my F1 score as big as possible. And then sure, you can just tune whatever you want, including class weight, and try to get the best F1 score, and that's totally fine. But often it might be hard to find a score that perfectly encapsulates what you care about. And then it might be that you do a bit of kind of manual tuning of class weight to get the trade-off between precision and recall exactly how you want it. Another question, how does F1 score relate to over and underfitting? So for all these scores, you can compute them on the training set and on the validation set, and you'll typically, if you're, whatever score you're using, if it's way better on the training set, then you're overfitting. And if it's about the same, then you're not overfitting. So we can kind of, we built that intuition with accuracy, but we can basically carry that over to all of these metrics. And so far, I've just been showing you everything on the validation set because that's what we care about more. But you could, everything we're doing today, you could do it for the training set as well. Okay, yeah, another thing to point out is that changing the class weight will generally reduce accuracy. So the original logistic regression was trying to get good accuracy. So here's the original logistic regression. Remember, dot score just computes the original accuracy. So that was 99.9 that we had like an hour ago. And if we take the class weight equals balance one, the accuracy went down. And that's because we have all these mistakes here. The accuracy just cares about the number of mistakes, which is this corner and this corner. And now we have 1,000 something mistakes, and before we had a lot less than that. But we may still prefer this thing with lower accuracy because we may prefer to get higher recall and just catch all of those frauds, get those fraudsters in trouble, or protect our customers is probably more what it's about. So just to keep in mind that if you do this and you're like, oh, but the accuracy went down, but I thought I was making things better. Well, accuracy might not be the thing that you care about. So maybe you made things better for you. And so scikit-learn score is not like the best thing ever to look at necessarily, because that's just computing accuracy, which again, may not be what you care about. Okay, I want to talk about why we have imbalance in the first place. So there's a couple of reasons why you might have class imbalance. One is because one class is much more rare than the other, which is our case here. There's just most transactions are not fraudulent, and so when we make a data set, we have imbalance. But it could also be because of your data collection methods. Like it could be that there's actually tons of frauds, but they're just less likely to be included in the data set. Not really realistic in this case. But I don't know, going back to the census one, maybe you had 99% of the people filling out the census had lower income, but it turned out that was just because they were more likely to fill out the census, or vice versa for higher income. And so you need to think very carefully when you encounter imbalance of why do I have imbalance? And that kind of informs how you handle it, right? Because you want to know what you're dealing with, and you want to think about your deployment situation. Because if it's just your data collection method, and in the deployment case, you're just going to get like 50-50 of the two classes, you might not want to mess up the whole class weight. You might just want to maximize accuracy because when it comes to deployment, there isn't going to be an imbalance, and you'll have kind of messed everything up if you dealt with the imbalance, but it was really just because you collected your data in a biased way. So think very hard about the deployment scenario and the type of errors you can get, and how much you care about the different types of errors. And like, I can't say it enough, don't just blindly look at score and accuracy and not think about anything else when you're working on classification problems, because in some cases that might serve you well, in some cases it might, but also don't blindly set class weight to balance, because in some cases it might be just fine, and you don't want to skew it in any particular way. So really engage with your subject matter, and it's not just a machine learning thing. It's about the problem you're working on. So that's what I wanted to say there. Here, I think I already said most of that. So yeah, I guess I did say earlier, I don't like to call the output of predict proba. I like to call them I don't like to call them probabilities. I like to call them probability scores. And here I'm just saying, yeah, they're definitely not really probabilities. Like, we can just change class weight and completely change all of those scores. And so, as I said a few weeks ago, if predict proba says 0.9, don't go to your boss and say, I am 90% sure, because those scores are kind of arbitrary, and changing the hyperparameters can change them. I have 3 more minutes left, so I'm a bit out of time. Let me, let's see. I'll just quickly touch on a couple of things here. Stratified splits is the idea that when you do a train test split or cross-validation, there's something called stratified versions of that, which makes sure it preserves the proportion. So if you have 1% frauds, it'll make sure each fold has 1% frauds, as opposed to just randomly splitting. And sometimes that can be desirable if you're worried about not preserving that. let me not go into that more in the interest of time. It doesn't make a big appearance on the assignment. And let me quickly talk about the hyperparameter search, which is on the assignment. And I'll just say that when you're doing grid search CV or randomized search CV or whatever, there's a parameter in there called scoring. And so you can tell grid search CV or randomized search CV, hey, I want to rank them by ROC, AUC, or I want to rank them by F1 score. If you just leave it by default, it's going to use the default scikit-learn.score, which is going to call accuracy. So on your assignment, on your homework, I ask you to look at F1 score. And so you'll need to set scoring equals F1. And then it'll rank the different hyperparameters by F1 score. Yeah, there's just a comment here that says the ROC, AUC are not affected that much by class weight. That's because class weight is kind of like changing the threshold, and ROC, AUC is like a summary over all thresholds, so it doesn't care that much about the threshold. And I know I'm super rushing now, but I just want to end on time and trying to get through the things you need to get started on your homework. So yeah, I think, so today we talked about, 99.9% accuracy is not always good. You want to look at all these different types of metrics. You need to think about what types of errors you care about more. And there are ways you can deal with this. You can use different scores. You can threshold, predict probability. You can use class weight. And this is kind of your job if you're out there doing machine learning, right? It's more than just knowing scikit-learn. Your job is to think about these questions and react appropriately. And there's no single way that I can just say, no matter what problem you're working on, use class weight equals this, because it's really domain specific. So I just want to emphasize that. And I'm out of time, so I'm gonna have to wrap it up here. Apologies for the rushing at the end.